All right, tomorrow in class, we are going to be starting a lab. And the first thing we're going to do is have a discussion. What is the objective? The objective is to determine the K constant of a spring. And I want students to think about how to design this lab if I said find it graphically. Well, the first step for any lab is to determine a math model. Okay. There's only two equations that you have that are related to the spring, and that is force of a spring and the potential energy due to a spring. Those are the only two equations that have K in it. So if you are trying to create a math model for solving for K, you only have two choices. So let's look at the potential energy due to the spring first. So I'm going to look at this one first. So here is this math model, potential energy due to the spring. Well, that's kind of hard to measure the potential energy due to the spring without knowing the spring constant. But what if I created a situation where I had a spring and I had a block that I compressed to some distance and shot the block and measured the velocity of the block right when it hit the x equals 0, okay? And I could measure the velocity using a photo gate. It's a tool that's used to measure a velocity at a certain spot. So a photo gate has a laser beam that runs across it, and I can measure the velocity right at that spot. So now, if I knew the velocity of the block at the spot where potential energy equals 0, I now know the initial potential energy of the spring has to equal the kinetic energy of the block final. And I can then use my definition of those two and develop me an equation for um, that relates K to the initial compression of the spring and the final velocity. The 1/2s cancel. K is what I'm looking for. I can measure the initial compression and I can measure the final velocity, and I can vary the initial compression. So that's awesome. The mass is constant, so that's fantastic. So I can change the x values. I can change the x values and then measure the resulting velocity of the block with different compressions. And then how would I graph this data? Well, I take that original equation, multiply it by 2, get rid of the half, rearrange it. This is just one option. X initial squared over V final squared equals mass over K. Well, that's a constant value, huh? X squared can go on my y-axis. V final squared can go on my x-axis. I can graph that, and the slope of that equals what? M versus K. There is a design of an experiment. Now, that's not an easy thing to measure, the final velocity, and we have to have a photo gate. What if I use the other tool or other equation? Force of the spring is equal to K times X. I could try to figure out how do I can pull a force on it. I just got to figure out what to measure. How do I measure the force? Well, there's lots of different ways. I can have a force meter. I have a force meter that has a digital readout. I have a spring scale where I could actually has a little dial, and that's actually our pivot lab. It has a spring scale on it. Or what if I turned the spring vertically and hung a mass on it, a mass that I can measure? I could see that by the free body diagram, the force of the spring has to equal the force of the gravity pulling on the block. If I know what the mass of the block is, I know how much force the spring is pulling up on it. And I could change the masses, mass 1, mass 2, mass 3. And so I know that the force of gravity, which is mg, equals the force of the spring. So I can actually calculate the force of the spring in those situations that's pulling up on the block for each block. Then I can measure with a ruler how far the spring was stretched. And I now have some pretty easy data. All I needed was a scale to measure the mass, and I needed a ruler. That was it, or a meter stick. Okay, what do I graph? Well, let's rearrange that equation. If you recall, I need to rearrange the equation with the two things that I'm measuring on one side of the equation, which is force of the spring and X. And I get this, force of the spring divided by X. Well, K is constant, so I put force of the spring on the y-axis, the compression, the stretch length on the x-axis, and the slope becomes a constant number and it's K. So now I have figured out a way to measure it graphically. So every single design of a lab has an objective, usually a math model. That's the number one thing for me personally. Then a sketch. You need a sketch that's labeled so that they can see what you're measuring. You are going to probably provide an example of data tables. You would have to say how you would analyze your data. In other words, trust me when I tell you, it's easier just to come up with a graph. And lastly, to provide a procedure. So measure the mass, place it on the spring, measure the X, repeat that for M2 through M4. Now, repeat the entire thing 2 times and then average your data. So what do I mean by that? So you will measure each X for each mass 3 times. That's a minimum. And then you will average that. So I ran out of space over here. You would have a table for average X. Now, why do we do that? You have to tell them that you will run 3 runs for each trial because you want to take an average in order to reduce error. Okay, so this is one of our main topics, and then we're going to work on BCHS Lab number 6, which I think will be due Thursday, and that's what we're doing in class tomorrow. I hope you're there because it's a good one, and I hope that you don't miss it. So anyway, that's what I got. Have a good day.